Now let's look at this example 8.1. That is to bring the memories of all these properties about continuous time Fourier series, okay? Kind of like a reminder. So it's really an interesting question. That does not give you a signal. Instead, it gives you all the clues about the signal. Then you basically, it's like solving a detective crime scene as a detective, and you have to use these clues to find out what that signal actually is. So let's, again, this is a good example to remind us of these properties about continuous time Fourier series, which are very similar to those properties to Fourier transforms, Laplace transforms, and so on. Okay, let's get started. So first of all, x of t is periodic. So that's the first clue. So that means x of t can be represented by Fourier series, right? And the fundamental period t naught is given 4, and the Fourier series coefficients are the set of a sub k's. This curly brackets means a set, okay? All right, so what can we get or derive based on this clue? Well, first of all, we know that x of t is periodic, right? And so then the fundamental period is given, and I need the fundamental frequency. That is 2 pi divided by the fundamental period. And in this case, the fundamental period is 4, so I have half pi radian per second, right, as the frequency. And another thing I'm told is that x of t has a Fourier series a sub k. So in other words, we have the pair of synthesis equation and analysis equation. So by synthesis equation, we can synthesize the signal x of t by linearly combining the basic signals in the case of Fourier series. We are using harmonically related complex exponentials whose frequencies are discrete, specifically integer times the fundamental period. Okay, in other words, they are harmonically related. And each case harmonic has a weight of a sub k, and we linearly combine them together, basically with infinite terms, right? Where k is an integer. Okay, that's what we get from the first clue. Now let's move on. Second clue. Well, a sub k is equal to 0 for any k that is above 1. Let's keep in mind that k is an integer. So that means what? So that means the only non-zero Fourier series coefficients are a0, a minus 1, and a plus 1. Okay? So that means effectively x of t is the summation of just 3 terms, where k goes from minus 1 to plus 1, right? Where we have the case harmonic with the coefficient of e to j k omega naught half pi t. Okay? Specifically, it equals to a0, right, times e to j 0 half pi t, which basically is 1. So we can remove that. So that's a constant term, but then you have a sub minus 1 times the e to j k equal to minus 1 omega naught half pi times t. And then we have one last term, that is a1 times e to j times 1 times half pi t. Okay, so that's the new clue. Okay, we sort of combined the first two clues together already. Okay, now let's continue the third clue. X of t is real. It's a real signal. Well, what do we know about the real signals? Let's try to recollect our memory. If x of t is real, this is something we have learned, that a sub minus k is essentially the conjugate of a sub k. We have seen this similar examples before where a sub minus k, the negative frequency term, is the complex conjugate of the positive frequency term, the corresponding one, a sub k, right? So back then we were given this property and we found that x of t is real because you can merge the real part and the imaginary part. So in this case, so the imaginary part cancel, the real part doubles. You end up having, just the real signals. And but going the other way around, we can use this property that if x of t is real, we have the conjugate symmetry. Okay, so that means we have one less unknown variable. We only had a0, a sub minus 1, and a sub 1, right? So we reduced the question of finding x of t down to the question of finding the only three non-zero Fourier series coefficients of this signal, a0, a sub minus 1, and a sub 1. Now that x of t is real by the conjugate symmetry. We have one less unknown. That is, we know that a sub minus 1 is just the complex conjugate of a sub 1. So now we only have two unknowns, right? Basically a0 and a sub minus 1 or a sub 1, which are complex conjugate of each other. Wonderful. Now, the fourth clue is kind of weird. It says that there's another signal whose Fourier series coefficients are b sub k, that is a complex exponential times a sub minus k. And that signal is real. Sorry, that signal is odd. Okay, that means if that signal is y of t, then y of minus t equal to negative y of t. So that means the signal is odd. Well, if a signal in the time domain is odd, what does it say about the Fourier series coefficients in the frequency domain, right? Because this k determines the k's harmonic, whose frequency is k times omega naught. Well, let's try to remind ourselves, right? What did we learn? Something about even and odd. I think, yeah, here we are. What we learned back then was that if the continuous time signal x of t is even, then the Fourier series coefficients a sub k is also even. We proved that together. So that's how we proved it, right? because if x of t is even, then x of minus t equal to x of t. Let's do Fourier series on both sides. On the left-hand side, we apply the time reversal property. We end up finding that a sub minus k equals to a sub k, which means a sub k is even. Similarly, if x of t is odd, then the Fourier series coefficients a sub k is also odd. So now let's come back to this question, right? This clue says that that signal is odd. Okay, so if the signal, right, is another signal with Fourier series coefficients b sub k, which equals to a phase shift version of a sub minus k, excuse me. Okay, if this signal is odd, right, by the odd symmetry, the property we just flashed back, by the odd symmetry, we know that b sub minus k must be equal to minus b sub k. Okay, but that is b. What do we know about a? We only need to figure out a sub 0, a sub minus 1, and a sub 1, right? Okay, let's just write them down and see what bk tells us about ak. Okay, so let's see. Let's again look at this expression relating bk to ak. Okay, and let's see if k equal to 0. If that's the case, b sub 0 is equal to e to minus j times 0 times half pi. I don't even have to write that. It has to be a constant, 1, right? Times a sub minus k. So, excuse me, that k is now 0. A sub minus k is a sub minus 0, which is a0. Okay? b0 and a0 are the same. Good. What if k equal to 1? If k equals to 1, we have b0 equal to e to minus j times 1 times half pi. A sub, excuse me, I had a typo here. Should be b sub 1, right? Okay, b1 is e to minus j half pi times a sub minus 1. Am I right? Okay. All right, so then what does it say? What is e to minus j half pi? If we think about a complex plane with real part and imaginary part being the two axes, and this is e to minus j half pi, where the exponent is purely imaginary. So this is a unit vector on the complex plane. The magnitude is 1, right? And the phase is negative half pi. So that means it is pointing downward. That is negative half pi, right? And specifically, it's with 0 in the real part and with minus 1 in the imaginary part. Okay, so let's see. All right, so now this green part will become minus j, right? Because j times minus 1. So that equals to j, and then we end up having minus j a sub minus 1. Okay? So that's what the first expression relating bk and ak tells us. But we also know that b minus k equal to minus bk. All right, let's see. What does it say? It says that we can also let k equal to minus 1. And then we end up having b sub minus 1, and then that's e to minus j times minus 1 half pi, which is half pi. That is this signal. Okay? And that gives us a j times a sub minus of minus 1, so that is a plus 1, so that is j a plus 1. Okay? However, we know more about it. We also know that b sub minus 1 should be equal to minus b sub 1. Okay? If we plug it in, if we plug the expression of b1 and b sub minus 1, what do we end up finding? We find that b sub minus 1 equal to j sub a minus 1, a sub 1, that equals to minus j 1. That equals to j sub a minus 1. Then this constant j is cancelled on both sides. If a1 equal to a sub minus 1, a1 equals to a sub minus 1. Well, that's another clue about a1 and a sub minus 1, isn't it? Let's see what we really learned. All right. So a1 and a sub minus 1. Back then, we learned the first equality about a sub 1 versus a sub minus 1. They are complex conjugate of each other. Then we learned that they're actually equal to each other. They are complex conjugate of each other, and they are equal to each other. How do you make that happen? Well, if you are not still not clear about it, right? If you can merge these two facts together, these two highlighted portion together, you cancel a sub minus 1, you found a1 equal to a1's conjugate. That means what? That means a1 is real, right? It's its conjugate, its complex conjugate is itself. Okay, so that's something let's keep in mind for the moment, right? Okay. What else? I still don't know A0, right? Okay, how do I find A0? Well, let's see. BK is odd, so B sub minus K equal to minus BK. Okay, so now let's start thinking about what to do with A sub 0, right? Because I only have 3 unknowns. It feels very close now that A1 is real and A1 is a complex conjugate of A sub minus 1. Well, if A1 is real, and A sub minus 1 is a complex conjugate of A1, that means what? That means A sub 1 is also real. Okay. And they are equal to each other. Okay, so one less unknown. Lastly, A sub 0. Let's see. What do we know about A sub 0? Okay, so what I have is this. B0 equal to A sub 0. Okay, let's use a different color. B0 equal to A0. Okay, now I know that B sub minus K equal to minus B sub K. That means what? Let K equal to 0. B minus 0 equal to B0. Excuse me. Equals to minus B0. So that minus 0 is the same as just 0. So B0 equal to minus B0. So that means what? So that means A0, which is equal to B0, has to be equal to minus A0 as well. Well, how can you make A0 equal to minus A0? Well, that means A0 equal to 0, right? So this is another derivation we had. Well, we only have one unknown now, because A0 is just a found. And A1 and A sub minus 1, they are equal to each other. Well, there got to be one more clue, right? One more clue that tells me what A1 or A sub minus 1 is. What is that clue? Well, a really interesting clue. The integral of 1/4 in an interval whose length is 4, right, equal to 1/2. Specifically, I'm integrating the square of x of t. The squared norm of x of t. The squared magnitude of x of t is basically proportional to its energy. Yes. So this is a periodic signal. We are integrating it in the interval of length 4. That is the fundamental period. Okay, and that 1/4 is 1 over T naught. So this reminds us what? This is basically telling us this integral is the energy in that signal, and then divided by the fundamental period 4 is the power. Okay, the power of this signal is equal to 1/2. But what property tells me anything about the power in the periodic signal? That is the last property we have learned, that is the Parseval's relation. Okay, so the Parseval's relation tells you that the power of x of t, the signal, can be calculated in the time domain, like the integral we see on the left, and it can be calculated in the frequency domain as well, right? By using the sum of the squared norms over the Fourier coefficients, and they are the same. Okay, well, that is wonderful. That tells what one more relationship among the Fourier series. Okay, so apparently what is being told here is something about the power. Okay, so 5, basically the last, right, is telling us that, this is on the left 1/4, right, interval over a length of 4, and then squared norm of x of t dt, and that is nothing but 1 over T naught, right, over the squared norm integrated over T naught. So that is a power. Okay, this is a power measured in time domain. Okay, so by the Parseval's relation, we can calculate power also in the frequency domain. We have the sum over all the frequency terms, and let's calculate the squared norm of the Fourier series coefficients. Okay, and in our case, we actually only have 3 terms due to property or clue 1. We have a0 squared norm squared plus a sub minus 1 norm squared plus a sub 1 norm squared, and this is the power in the frequency domain, and they should be equal. Okay, so they should be equal to each other. Okay, all right, so they should be equal to each other. What is the power in the time domain? This was given 1/2. Okay, don't forget that a0 equal to 0. Okay, let me rewrite this part, wasn't very clear. We should have the norm of a0 squared, and that's simply 0. How do I get that? Right here, a0 equal to 0, isn't it? In the fourth clue. And a sub minus 1 and a sub 1, first of all, they are both real, right? And secondly, So to help you see that, I can use this one, right? A0 squared, just like what you see up above. And secondly, because A1 and A sub minus 1 are both real, I can take away that double bar, so I don't need norm anymore. Right? I don't need the norm anymore. Even if it's absolute value, it doesn't matter because I have the square. Then if I add them up together, I end up having 2 times A1 squared. Isn't it? Okay. So that means what? That means the last clue, 2 times A1 squared equal to 1/2. A1 squared equal to 1/4. And A1 could be plus or minus 1/2. Okay. All right. So, wow, that is really the last unknown Fourier series coefficient. Okay, now let's put them all together. What is x of t? We have the solution now. So x of t is, well, in fact, even though we were told that there were only 3 non-zero Fourier series coefficients, but then we find out that actually one of them, a sub 0, is also 0. So we end up only having a1 and a sub minus 1, and they are equal to each other. So that means what I need to have is the same coefficient, right, times e to j minus 1 half pi d plus minus e to j plus 1 half pi t. This 2 corresponds to this 2k values. Okay, and then we should merge the same plus minus 1/2. Then we end up having e to minus j half pi t plus e to j half pi t. And these two complex exponentials are complex conjugate of each other using the Fourier's formula. Apparently, what we can see here is what's in the parentheses is two times cosine half pi t, isn't it? In the end, this 2 and 2 cancel each other, is plus or minus cosine half pi t, and that is our final solution. Okay, so x of t equal to plus or minus cosine half pi t. Whew. We took it slow and used all the clues. And while unraveling each clue, we applied multiple, or sometimes one, sometimes multiple properties of continuous time Fourier series coefficients. And then that is the final solution. That is just plus or minus cosine half pi t. That is the signal that we have been trying to figure out with all these 5 clues. I hope you have enjoyed this example.